So this is lecture number 13G, and we are going to see this reason also. Over here it's actually quite hot, I can't speak with this one. So today we have the contents over here as the shunt motor speed equation, which we are just going to see as well, and we are going to see the speed torque curve of this one. And any machine, whenever you are going to actually compare it, we have to actually find out the speed torque curve, and then we are going to see the speed control techniques over here, and then we are going to see this is the same VA, VF and other methods characteristic curve. This is very, very important. This one is very much important, and please kindly pay attention when I'm talking this one, because this is going to be from the book, but still. And then the field loss relay. This field loss relay is actually the answer for the question which I just asked you, that if you are running your DC machine and accidentally one of the wires comes out, which wire is that, we will discuss it just now. And when that wire comes out, the fuse gets burns. And why the fuse gets burned, that answer will be answered also today. But before that, if I go on, let's talk about the shunt motor. Now, I guess I told you in the previous also, and I guess in the lab it has also been told to you, that a shunt motor and a separately excited motor, they both, so if I'm talking about the shunt and the separately excited motor, so either a shunt or a separately excited motor, they both are going to have almost the same characteristics. Why? Because if I draw a shunt motor in front of you, for example, this is your RA. You have done this in your lab as well. This is your field winding, and this is your supplied voltage over here. And since this is shunt, because everything is in shunt over there, so if I just show this one over here, this is your RF, this is your LF, this is your RA, and since this is a motor, so this EA over here is the back EMF, and this is VT, and certainly this current is IL, this current is also IL, certainly this one is IF, and this one is your IA. And I guess I don't need to tell, according to your Kirchhoff's law, that IL is equal to IA plus IF over there. And if you are interested in finding out IF will be certainly equal to VT divided by RF. This is the steady state point, which means that if this is a DC working over there, the inductor is going to behave as a short circuit. I'm not talking about any transient analysis over there. So I guess you already know this one, that VT is equal to EA plus IA RA is the motor equation for your shunt motor. And if you have a separately excited motor, almost same thing. The only thing different is this, that there are now two supplies required over there. And when you have two supplies required over there, certainly this means that this time now it will be something like this, and this will be your field winding, and certainly some inductance over there, and this will be again a supply, and that supply, as we all know, will be certainly equal to VF over here. This one can be called as VA, or it can also be called as VT. Totally up to you, but VT is since common in the shunt motor also. So this is your RA, and this one is your again back EMF EA, and this one is your RF, this one is LF. Now one thing which I have not yet included is the shunt branch, which is the shunt resistance which you are using in your lab for speed control. Those who have done the experiment, you must be having an idea that whenever you are going to have the speed control method, you are actually going to add a resistance which is variable, and you are actually going to call it R shunt. Why? This is actually in the shunt branch. So when you are going to change this one, certainly this means that the IF current is actually changing over there. And if I attach this one similarly over here on this branch, so this is your again R shunt, and certainly this current is IF over there. So again, this time you can have actually a little change over there. So now this time IF now will be equal to VT divided by RF plus R shunt, because now you have added another resistance. Same equation applies for the separately excited, and I guess I don't need to repeat this one, that if you are going to take the KVL equation of this loop over there, so this KVL loop equation is on this one, this is going to be again similarly VT equal to EA plus IA RA. So if you write down the KVL equation, this will be similar over here. The only thing change in between these two is this, that IA and IL is totally not equal to IF. They are not equal over here. They don't have even any expression because they are separately excited. But if you talk about any industry, wherever a DC machine is being employed, you will always find mostly a shunt motor being used. The only reason it has one supply. Otherwise, if you have a separately excited motor, you will require two supplies over there, and two supplies make it difficult to actually run it and to maintain that supply part over there. So now this is shunt machines or separately excited machine. Now, when I'm talking about any machine or motor, whenever you are going to talk about any machine, the first thing that you are actually going to talk on is the magnetization curve. Now, those of you who have actually done one experiment that is relating to the ascending and descending order of your machine. Now, what is a magnetization curve over here? Let me just talk on this one. It's a little bit away from our topic, but since we are talking on the machine, so a magnetization curve. Now, those of you who have done this experiment in the lab, what you have been doing, so what you have been doing up till now, you had a field current on this side and you had EA on this side. And there were two conditions in this experiment. Those of you who still remember it, you will verify this one. You are going to start your field current from zero. And supposingly at zero field current, you start it over here. Let me use some other color over there. And you will plot it after every interval, and then afterwards you will reach a maximum point. So that maximum point supposingly is reached at approximately 200 milliampere. Now, when you are going to plot this from 0 to 200 milliamperes, the only condition is this, that your machine speed has to remain constant. Now, why this is so? Because we have done this equation proof previously that EA was equal to K phi omega. So whenever a magnetization curve is being formed, this omega has to remain constant. K is already constant. So these two are actually going to remain constant. So IF is certainly proportional to your flux. So this means that your flux versus EA, this curve is going to be plotted. So when you are going to run this, now how you are going to actually do this experiment, those who have done it, you have done it by having a motor coupled with a generator. So a motor is actually running at some speed, maybe like 1400, 1500 RPM, whichever you have fixed it, and you are running that generator. And in that generator, now that generator is now working as a generator with a shunt resistance in the field path. Now, when you are going to change that resistance, you are actually going to change it from 0 to 200 milliamperes in the lab. And once you have increased the value, you are not going to decrease it. And supposingly, during this first half of this experiment, or even in the second half, light goes off. There is a load shedding something part. You cannot do this experiment. You have to start it from zero back. Now, why this is so? Why these instructions maybe have been given to you in the lab? The only reason for this one is this, because when you are increasing the current from zero to some value, you are actually aligning the domains of your ferromagnetic material inside the poles. So when they are aligned together, you cannot decrease the field current, because now you have to go up till the maximum point, and then afterwards when you are actually going to decrease from 200 milliampere to, supposedly you start decreasing it, you will have actually something like this trajectory being followed over there. If you can go to up till zero, this trajectory will be followed over here, and this curve will be called as the descending curve over here. Now, this ascending and descending curve difference is actually telling you that this is actually the retention of magnetism inside the poles, which is the ferromagnetic material of your machine over there. So this magnetization curve is plotted with some assumptions that your speed is constant, and during this all experiment, one person, whoever is doing that experiment, has to make sure that your speed remains constant. And how it can be maintained constant? By the motor which is attached over there. So when you are going to increase your field current from 0 to something 200 milliampere or 150 or whatever that range is there, so you are going to reach this maximum point, and then afterwards you are going to start your descending journey. And the same rules apply over here, that when you are decreasing it, you are actually going to decrease it in steps over there. And if you decrease it a little bit further than you're required, you cannot go again back now. Because if you are going to actually, supposedly, for example, if I have something, you are actually increasing it over here, and okay, you find out you have missed some point over there. If you start and make it back, it will follow this trajectory. It will not follow the white color path. And then if you will again increase it, then it will follow something like this. So the values will not be accurate if you align and de-align during your whole experiment. So what you have to do, that you have to increase in one direction and then you have to decrease in the other direction. And in experiment, those who have done this experiment may have witnessed it, that you not even have up till 0. Why the 0 is not there? Because the magnetism inside the machine, it cannot be made exactly equal to again 0. The field current cannot be made equal to 0. So you may only get up till this point over there. So up till this point, this curve can be plotted. But this ascending and descending curve, this is ascending and the other one is your descending curve. So these two curves are actually telling you that your machine is having some retention, and this curve is called as the magnetization curve. Now what they have done in your book on, I guess on page number, the start of this chapter in somewhat on page number 469. G, any question? Field current cannot be made 0 in shunt motor or shunt generator. How you can make a field current equal to 0? Because if you make field current equal to 0, this means you have effectively taken out the magnetism out of it. The only thing that you can take out is actually a separately excited. For separately excited, you can make this up till this point over here. Otherwise, in shunt generator, you cannot do it, because if this is a generator, now supposingly if I want to convert this one into a generator, see this very carefully. So I don't have this supply over there. Now this time, if I mark it for supposingly some different color over there, let me use some other different color. So this time now IA will be like in this direction, IF will still remain in this direction, and IL will be now in this direction. And now here in this special experiment, you are not going to have any load attached. You are just going to attach a voltmeter. Why? Because you are actually trying to find out the VT voltage over here, and this VT is approximately equal to EA. Why? Because IA is very, very small. So the generator equation, if you remember it, this was equal to EA minus IARA. So when IA is very small, this subtraction is very, very small. So we assume it that VT is approximately equal to EA, because EA cannot be practically found out by any means. Okay, because that is internally induced voltage over there. The only thing that you can measure is actually VT over there. So this, in this experiment, you cannot make your field current equal to 0, because if you make field current equal to 0, this means that effectively you have taken out this branch totally. So only in separately excited motor you can do this, because here you have a supply over there. And if you can make the supply variable, or make this shunt resistance equal to infinite resistance, then this means that your field current will be equal to 0. So maybe in separately excited, you can draw this whole magnetization curve with ascending and descending curve, but in shunt generator, you cannot do it. And this magnetization curve, though plotted from a shunt generator, but applicable for the motor also. Why? Because this is the same machine which is going to be working as a motor in some case. So in your book on page number 469, what they have done, they have only given only one curve over there, and that is the ascending curve which they have given over there in this direction. Why? Because they are not interested in the generator action of that machine. They are only interested in the motor action. So whenever a motor is being given to you, there is a lot of numericals in this chapter which are talking about or taking into consideration that what is EA at that particular speed. So a magnetization curve that will be given to you, it will be given at some speed supposingly, and that speed will be equal to 1500 RPM supposingly at our lab. So this will be the blue color curve. Now supposingly, if I change my speed to supposingly 1000 RPM, then what will happen? The speed is reduced according to this equation. When speed is reduced, flux is changing, K is already constant. So what I am going to get, I am going to get something, a curve like this one over there, because it's not going to be totally linear, because the speed is a factor over there which is going to take part. And then if I have another, let me use another color, supposingly if I have this one and I reduce the speed to something like 500 RPM, then maybe my curve is just going to be like this over there. Why? Because speed up till some certain point, it's going to be a factor, but otherwise afterwards, then this is not going to be important, because here the speed is very, very small, so it's not generating any much EMF inside your generator action. So magnetization curves are speed dependent, and they are dependent upon you are making them on the ascending order or your descending decreasing order over there. Now, keeping that into view, when you have a magnetization curve with you and you have been given for that motor over there, now the next question occurs that how you are actually going to run your machine, your shunt motor. Now I'm taking this back to your shunt motor example because we are today talking on the shunt motor case over there where this is VT and I'm talking about this this current IL, this current IA and certainly IF, which is in the same direction. So I want to now find out the motor speed equation. For this purpose, what I have over here, I have the first general equation of my motor, that is Vt equal to Ea plus Ia Ra. See this, listen this very carefully because this is very important. Vt is equal to Ea plus Ia Ra. Now I know from my previous chapter that Ea is equal to K phi omega. This is also elementary equation. So I can put this Ea in this relation. So this can be now changed to Vt equal to K phi omega plus Ia Ra. Now why I am doing this? Because Ea cannot be found. It cannot be measured. Okay? It's no way you can actually measure it because this is the internally induced EMF inside your machine. And in our motor case, this one is the back EMF of your machine. So Vt is equal to K phi omega plus Ia Ra. And now one another supposition over here, because here Ia is the current. And we know if more current is there, more torque is there. So what is the equation over there which I am going to put? Since torque is equal to K phi Ia, from this relation I am taking Ia equal to torque induced divided by K phi. So from here, this relation put over here in place of Ia, my equation now becomes equal to Vt equal to K phi omega plus torque induced into Ra divided by K phi. Now if you see this relation, what I have done over there, I have now only very few variables in this equation. What are those variables over here? I have Vt, and certainly this is changeable. Then I have our flux phi. Certainly this is also changeable with the field current. Then I have some constants which are not going to change throughout that machine is working. One is K. The other one is your Ra resistance. These two are not going to change when you are working on the same machine. The only thing that can change is actually Vt and phi over here. The other things which are over here as variables are the independent variables are omega and your torque induced over there. These two over here are actually our output. And if you see very closely, this omega and this t, I can rearrange this equation and find it out as omega equal to Vt over K phi minus, now this overtaken over on this side, I just simplified it over here. So this is minus Ra over K phi square torque induced. Now what is this equation telling me? This equation has torque over here on this side and speed over here. So what this means, our machine requires how much torque? Just put in this equation, feed in the value of Ra, feed in the value of K, feed in the value of flux phi and all these attributes and you will get your speed. So this equation is the speed torque equation of your machine. And if I want to actually draw it on a y-axis curve or x-axis curve over there, this is going to be an equation of a straight line. How? Because y is equal to mx plus c, we all know is the equation of a straight line. And for those who still don't remember it, m was the slope, x was your x-axis over there, the value, that is the dependent variable, and c was the y-intercept. So this one over here, this was the equation with the slope equal to m, plus m certainly because the slope is going upward. So y was the output variable over there on the y-axis over there. Now our equation over here, this equation, you can see a negative sign. So certainly, and what is our variable over here on the x-axis? I have torque induced. So I have to rearrange this equation, and this rearranged equation now becomes equal to omega equal to minus Ra divided by K phi whole square. So what is this term over here? Minus Ra divided by K phi whole square is actually the slope, and this is negative. This means that my speed is actually decreasing down, and here then I have plus Vt divided by K phi. And what is this Vt by K phi? Vt by K phi is the y-intercept over there. So when I'm going to draw this curve over here, this curve is going to be something going down like this. This is a negative slope over there. So this slope over here is equal to minus Ra divided by K phi whole square. This is the slope, and at this point, this is equal to Vt divided by K phi. This is the y-intercept over there. So what this curve is telling me, that as your speed, as your torque demand of your machine is going to increase, in other words, you are increasing the load on your machine, your speed is decreasing. So if you are trying to find out now the speed regulation of this machine, what you will do at this point, you are going to find out your omega no load, and supposingly this is the full load, so I can call this one as the full load torque. So at this particular point over here, I can call this one as the full load angular speed. So my speed regulation now will be equal to omega no load minus omega full load, and taking omega no load as reference and then converting it into the percentage. Similar thing, if you want to convert your y-axis into n, then you can have the same. Ji beta. Torque induces the requirement from the machine, that how much torque. Dekho, if you are applying a load on the machine, if machine is capable of supplying that load torque, it will produce that torque. If it cannot produce that torque, it will go to a standstill. So what happens? आपने lab में experiment किया है for a load test of a shunt motor or something like that. How you have done it? You have a shunt motor, you have a shunt generator attached over there, and as you increase the load on that shunt generator, your motor takes more current. Where that current is going? That current is going on the production of more induced torque. So this equation over here, that torque induced is going to be equal to load torque, will remain every time true for steady state condition. I'm again repeating, this is very important point, that whenever there is going to be a load increase on your motor, your machine will increase its torque so that it becomes equal to T load. What is T load? The required torque from the load. वो load क्या है? In our case, that load can be a generator which is having some load, or maybe some turbine which is actually being tried to run, maybe some pulley that is actually lifting water from a well, or maybe anything that is actually requiring a revolving machine or motion over there. So your torque induced, so this on the x-axis I have my induced torque, and in steady state point, again steady state point, maybe in transient conditions a point will come when this T induced will sometimes become equal to T load. This is very important. This will always remain in steady state. This one can be possible in transient, and when this will happen in transient, your speed will increase. क्योंकि आप load आपका required है, supposedly it requires 4 Newton meter torque, Newton meter units of torque, and your machine is now producing supposedly 4.2. So इसका मतलब you are exerting more turning effect from the machine, the motor speed will increase. But that will be only for a transient time. The motor will adjust its torque according to. I will just show you. Today's lecture is very informative. The next part over here, where you are actually going to see the transient behavior of your machine. That if your load on the machine increases, how it actually behaves over there. But overall, at present, this omega equal to Vt divided by K phi over here is the y-intercept, and the other one is the slope.
Is graph and Vt or phi constant?
Exactly. Vt and phi, they both are constant. Now, supposingly, if I change, now very simply, without going into the next topic over here, in this equation, I don't change anything. I only change Vt. I decrease my Vt. How will the curve change? Same curve equation, I change my Vt. I decrease down my Vt. What will happen? How will the curve change? The curve will go down, which means, supposingly if I draw it with some other color over here, the curve will be going down, but with the same slope. Why? Because this Vt by K phi over here, this one would be corresponding to Vt dash by K phi. And what is Vt dash? Vt dash is smaller than Vt. So what is this telling you? This is telling you that if you change your voltage applied on the armature, your speed can be changed. This is the first method of speed control which we have done in the lab, and this is the same equation over here where it's telling you that you can change the y-intercept. What does the y-intercept change? Y-intercept changes the no load speed also, and also the full load speed. So now you can see the slope is still the same. Kiska? Ek second. Now one thing very important, I have changed the Vt, but practically this Vt is not going to be changed practically. I am going to change the voltage applied here. ठीक है, अभी हम इस पे बात करते हैं. Just now, good answer, good observation over here. Because if I am going to change Vt over there, the field current will also change. So the point over here is it that you are actually going to change this one over there. That's why I told you that these two machines are Same over here. Why? Because here Vt changes, only armature current changes. The field current does not change. So when you are going to change Vt over there, you are actually going to change this voltage over here, and we call this voltage as Va. That is the armature voltage. And that's why in your experiment, what you were doing when you were changing the applied voltage, you were changing the R shunt also, so that the field current remains constant. And that field current remains constant means that field current is constant and flux phi is constant over there. So I hope you have an idea what I mean by this y omega equal to the speed torque equation. And this speed torque equation over here is telling you that your shunt motor or separately excited motor, they exhibit a negative slope and certainly a positive speed regulation. Why positive? Because certainly omega no load is greater than omega full load. If this characteristics was something like this, then certainly you would say that your speed regulation was negative. Why? Because then at no load, the speed was smaller. At full load, it would be larger. But there is only one machine which we'll be discussing in the next lecture. So the speed regulation for shunt machine and separately excited motor is positive, and this is the characteristic curve. Now, in the last lecture, we talked about the armature reaction on Friday. What was happening because of armature reaction? There was a net flux decrease over there because of the armature reaction. In this curve, we have not taken that into consideration yet. But if we take that into consideration over here, now see this very carefully. Now over here, if I take armature reaction without, my curve is going to be a straight line like this. But if I take armature reaction into consideration, we know armature reaction kicks in after some point when Ia becomes a little dominant, which means when Ia is dominant, then this means that your flux phi A is going to be dominant over there. Then this phi A plus your phi F, and then you are going to get something phi R in your vector form over there. So what happens over there, as you can see closely over there, at this point over there, this green dotted line over there marked, at this point armature reaction kicks in. So what happens? Because of armature reaction, your flux decreases. And we all know in this equation, when flux is going to decrease, what is going to happen? Our slope is going to increase or decrease. This is negative. Ye negative hai. This is negative over here. This is a negative value over here. So what will happen? You are going to have a speed increase over here. That is, the flux is decreasing. So you are going to have your speed increase. Now this is a totally non-linear behavior that is happening over here. Why? Because previously up till now we have a straight line equation, but now over here after some point we can see that with armature reaction the speed is now increasing. And if you continue to move your machine, it will not follow a line equation or not follow a steady state linear analysis over there. This is a non-linear analysis that has to be done over there. So just read this term. Any effect in the MMF in a machine will have a non-linear effect on EA. This is very much important. What this means over here, that if there is any effect in the magnetomotive force of your machine, there is going to be a non-linear effect. Why? Because we assume that this curve was plotted with phi constant. But what happens after this point, the torque corresponding to this one, your Ia is so much that at this point, your armature reaction is now taking place. And as it is increasing, you can see this difference is increasing. So when this difference is increasing, this is telling you that your flux, on this flux phi is actually increasing over there, decreasing over there. So when this flux phi is decreasing, your speed is increasing over there as shown over here by this curve over there. Now this armature reaction, we know this is going to be a detrimental thing, and this is telling you that when your load is going to increase or whatever, your armature reaction is going to make your speed increase. Now, can you answer one question at this present time? We have just seen that by increasing the load, armature reaction kicks in. But what happens due to armature reaction? Speed increases. So will this continue? The trend will continue if the machine is loaded, or a point will come when this will actually stop, and why? Anyone? Question is this, that we have just seen it, that with the load increased, the armature reaction increases, and with the armature reaction increases, we can see the speed is increasing. Okay? So it's not following the same straight line. So can this be possibly said that if the torque on the machine is increasing or the load torque is increasing, can we say that due to armature reaction the speed will continue to increase, or maybe it can be possible that it can go like this. Why? Technically, what you are doing over there, the y-intercept over here, that is over here, is also changing over there. So every point when you are going to have it, it will still have a downward trend, but never ever it's going to have. And a point will come when your machine will be almost at so much field armature current that this armature reaction is going to actually have your phi net so small that machine will not be possible to actually run. It will not be able to produce that amount of torque, and your machine will be actually covered up till this point, which means that the machines are not designed beyond this value, so that the armature reaction is just going to stop over here, and this is going to be your full load point. Remember, in this whole curve, I told you in this just last one that this is your full load point. Similarly, in this over here, this can be the full load point over there, where your full load torque is actually going to be produced over there. What is full load torque? Corresponding to full load torque, if I write it down, your full load torque is equal to K phi IA. And what is IA? This is the full load or rated current of your machine. So in your lab, you have your armature current rated at 3.5 ampere. So this means when you want to find out the torque, you need to find out flux phi, you need to find out K and put in IA as 3.5 amperes. That will be the full load torque over there. As just a guess, I don't know how many of you can be able to do it. Any one of you, you're doing experiments in the lab, try to give me the maximum torque of our machines in our lab, DC machines. I'm talking about the 400 watt machines. It's not written on the nameplate, but just try to find out what is the torque maximum of your machines. You can do this one with some reverse engineering and some data which you have it from your experiments, but try to find out. Take it as a bonus question. Whoever does it first, I will ask Mr. Rina not to give the value automatically, but try to find it out from your reverse calculation, what is the torque. Whoever does it will get some one or two marks, absolute marks in your whole grade. So this is a bonus question open to you. In the last lecture also, in section C, I gave this bonus question and one of the students actually did it also. So for you also, the question is this, that in our lab, what is the torque maximum of our DC machines, which are 400 watts machines? What is the torque? What is the value in Newton meters of those machines? Try to find it out. You have the equations with you. You have to just do a little reverse engineering and you have to find out that what is the torque over there. It's not written on the nameplate. And any manufacturer in the world never is going to write down the torque of your machine. They are only going to tell out the horsepower, or they are only going to tell you the input power of that machine. They are never going to tell you that what is the torque in exact Newton meter values. They are only going to tell you that, okay, this is the horsepower of the machine. This amount of horsepower is being taken up by the machine, and assuming an 80% or 90% efficiency of your machine, you can assume the output value over there. But as far as your lab is concerned, your lab machines are deliberately made a little lossy so that you can have or plot their characteristic curves. That's why I told you in the previous class also that your DC machine's efficiency is not more than 60 to 70%. In fact, the maximum which I have actually practically measured is 64%, not more than that. But try to find out the torque, as I just told you over there. So again, just a little slide over here for your armature reaction. As you can see, armature reaction खत्म कर दें तो कर्व सीधी है. So if you are having compensating windings in your machine, your curve will be simple, straight like this, straight line. But again, as I told you, compensating windings are only applicable when you are having a big machine and you can bear the cost of those compensating windings, then you can have it. Otherwise, this curve is certainly going to go up a little because of the armature reaction over here. Okay, just a little few words about armature reaction again. If you have armature reaction taking place inside your machine, so what happens over there? What is NFIF? NFIF is the, NF over here is the number of turns of the field winding. IF over here is the field current. So what this means that NFIF over here, NFIF is the MMF of your field winding. So what I am doing over here with NFIF, which is actually the MMF of your field winding, minus this armature reaction MMF, which means that armature reaction MMF that is actually being subtracted from the total MMF of your machine. So what happens, this is your net MMF which is responsible, and this is the same F which is correspondingly producing the net flux in your machine, and as I told you, because of armature reaction, this net flux is decreasing down. So this means that when your net flux is decreasing down, your total torque of your machine is actually also decreasing over there. So if I convert this relationship into by dividing it by NF on both sides over there, this NF and NF cancelled, so I have NF over here, and if I also divide it by NF over there, so this is the hypothetical equation. You can't use it actually from some practical values, but this is the hypothetical equation where this is written as IF hysteric. Now what is this IF hysteric over there? This is the equivalent field current that would produce the same output voltage over there, which means that you know your field current, which is actually flowing inside your machine, and you know your magnetomotive force because of your armature reaction, divided it by NF over there. So this is giving you IF hysteric over there, which is actually telling you that the equivalent field current that will produce the same output voltage. What I mean by this, if I go back to your magnetization curve over here, what was happening over there? Supposingly this is my magnetization curve which I am interested in. So supposingly if armature reaction was not happening previously, what was happening? Corresponding to this value of field current, I was getting this value of EA. Now since I know armature reaction is happening inside my machine, so what happens that your field current is going to be, or effective field current is going to be decreased. What I mean by effective, corresponding to this field current, supposingly this was equal to some 180 milliampere, and corresponding to 180 milliampere, I wanted my EA supposingly to be equal to 140 volt. But since armature reaction is taking place in your machine, your effective flux is decreased. So what is happening? You are not getting 140 volts over there. You are going to get something a little less over there. Supposingly that value is 130 volts over there. So corresponding to that 130 volt, this current over here which you are getting, supposingly this value is equal to 140 milliamperes over here. This 140 milliampere is that IF hysteric over there, which is producing that 130 volt. So that can only be calculated from your magnetization curve. If IF is there, you have your 140 volt output over there, but practically you are only getting 130 volt output, which is corresponding to 150 milliampere. So what this decrease of 180 to 140, this decrease is corresponding to that armature reaction divided by NF over there in that equation. Now this is happening inside the machine, but practically you won't see at 180 milli. Your current will be still going at 180 milliampere. This is very important. When you are going to measure the machine current, field current, it will still be 180 milliampere, but it will be only producing flux corresponding to 140 milliampere, because the remaining is lost as armature reaction over there. So this is the same thing depicted in this relation over there. So this is actually telling you, this IF star is actually telling you the equivalent field current that would produce the same output voltage over there. Okay. Any questions with this, G? The last thing before I go on towards the speed control is this, that is the constant speed. Now, if you have a constant speed omega, you have this magnetization curve, which I have plotted over here, like this over there. So this means when you have EA equal to K phi omega, or EA equal to K dash phi N. Now, when you have speed constant, this means N is also constant, K is also constant. So when you have two relations over there, this equation is quite possible over there, which means that EA equal to NM, where NM is the speed at one certain point, and then EA dash is the speed or EMF at one certain point. So what this means over there, this equation, that supposingly you have been given a machine and you have been told, supposingly you have been told with EA equal to supposingly 100 volts, the speed was approximately equal to 1000 RPM. Now you have been given this value, and you have also been given this magnetization curve. Now corresponding to this magnetization curve, you are asked over there that what will be your EA at 800 RPM. So you can use this relation over there, assuming your flux is constant. K is already constant because this is the same machine. So you can use this relation over here to find out your EA dash from a curve over there. Why this is so? Because you have made a magnetization curve for one certain speed. The other magnetization curve will be something like this. So you can find out your EA dash from this equation over here, because here flux phi and K, they both are constant. But this will be only applied if your field current is constant. Otherwise, if it is not constant, then you cannot apply this assumption over there. This equation is being used in a lot of end problems and some examples also. So this is very important. So in the question, you will be asked that, okay, this is the speed, this is the EMF that is being produced in your magnetization curve. Kindly tell us what is going to be the EMF at 800 RPM. Keeping the field current constant, which means flux phi is constant, K is already constant. So you can easily find out by simple, because you have now one unknown quantity and 3 known quantities over there. Now, coming on to the speed control. Now, this is very, very important, and I am going to do the difficult part first, because time I have less over there. Now, the first thing over here is field resistance. Now, let me just copy this diagram actually. This is a very important diagram. So, I have this diagram, and I have, oops, sorry. Okay, so over here, I have this one, and I am not talking about the generator, I am talking about the motor over here. So I have the motor over there. Let me just take out this blue color ones over here. They are not important to us. So over here, I have this shunt motor. Now I am talking about field resistance change. What this means over there. Listen to this very carefully. In this diagram, what I am doing, come on. What I am doing over here, I am increasing this R shunt resistance. So what is going to happen? The total resistance of your field winding, which is equal to R shunt plus capital F, and I can write it as R small f equal to R shunt plus RF capital over there. So this RF, because of this R shunt, is decreasing down. So when this is decreasing down over there, what will happen? The first thing you are going to get over here is this, that when your field resistance is going to increase, because of this, your field current is going to decrease down. This is the first change. Now, I am doing this analysis on a transient basis. I am not talking about a steady state analysis. I am doing it in millisecond times over there, which means that I have done it, and just at the very instant, what will happen? Now, since RF resistance is increased, your field current has decreased. So, when your field current has decreased down, your flux phi of your machine will decrease down, because they both are interrelated to each other. So your field current is going to decrease down, your flux is also decreased. Now, as soon as your flux is decreased down, your flux decrease is going to make your EA, which is equal to K phi omega. Now here what is happening? Your flux phi has decreased. So what will happen? Your EA will decrease. Okay? Your EA has decreased down. So your flux phi has decreased, your EA is going to decrease down. Now in this machine, what is your EA? If you see very closely, this EA is the back EMF. And what was this back EMF doing? This was actually not trying to have a lot amount of current flowing inside the armature. That's why it's called as back EMF, because this EMF, this was working as a back EMF, so it was not allowing this current to flow inside it. So practically what was happening, if I rearrange this equation can be called as, if I write it down, this is IA equal to VT minus EA divided by RA. Just rearranging this equation, and this equation is telling me that whatever value of VT you have, and it is constant, I am not changing it, EA, if it will decrease, your IA will increase over here. And why has EA decreased? EA has decreased because your flux phi has decreased. So the next thing which I am going to happen over here is that because of your, let me use the other color. So this is EA, when it decreases down, the next thing which is going to happen, I am writing the whole equation. This is IA equal to VT minus EA divided by RA. So what this means, that now your EA has decreased. So what will happen? Your IA will increase. So what this happen? The supply current is actually going to increase. Why? Because this IA is being provided from the supply. So what this means, that IL is actually increasing. And on the other side, your field current will remain the same. Why remain the same? Because this is connected across VT. VT is not changing. So only thing that is changing is IA over there. Now the interesting thing arrives over there, that if your IA has increased, the next thing which you are going to happen, if I use this one, IA has increased, then what has happened? Your torque induced, which is dependent upon K phi IA. Now this is a very, very important thing happening now. What IA has increased. So what I can say that your current IA has increased, but at the very same time your flux has decreased. ऐसा ही हुआ जी, flux क्योंकि decrease हो चुका है RF के बढ़ने की वजह से, and IA has increased. So what is the quantity for torque? Is torque going to increase or is torque going to decrease? Now, to answer this question, I can give a deliberate answer, but to answer this question, I am going to take one example over there. For example, what I mean by this, let me take the example from the book over here. It's going to be easy. I have a same machine over there. What this means over here, I have a VT of approximately 250 volts and EA is working at approximately 245 volts. The machine is working in steady state, which means the machine is working at some normal load, nothing happening over there. So at this point over there, let me call it as point A. So at point A, the machine was working at a VT of approximately 250 volt. Your EA was approximately 245 volt. So what is happening, and your RA resistance as given in your book, I am taking the resistance of the lab. So not the lab, actually the book from over here, 0.25 ohm. So you can see practically your lab machines, they have a resistance of 8 ohms. So they have been deliberately made large a little so that they can give you a lot amount of resistance drop and losses over there so that you can actually plot the characteristic curve. Practically in the industry, your resistances are always going to be very, very small, sometimes in milliohms or even microohms also. Okay, coming back to this one, I have my VT, I have my EA, I have my RA. So at this particular point, if I want to find out IA, your IA, as we all know, is equal to VT minus EA divided by RA. And if I plug in the values over there, this is equal to 250 minus 245 divided by 0.25. So this is actually equal to 5 divided by 0.25. And I hope this comes out to be somewhere 20 amperes over here. So this means that your armature is working at approximately 20 amperes of current over there. Now this is your point A, which means the machine was working in steady state. Now over here, if I just write it down, what I do at point B, what I have done, I change my RF resistance, which means I am increasing my RF resistance, which I just done in the first step. And because of that, your field current has decreased down, and that field current has effectively also reduced your flux. Now, assuming that your machine was working at steady state point and assuming it that your field current was decreased by 1% and this flux also decreased by 1%, assuming it that your machine was working in the linear portion of your BH curve. Okay? What I mean by this, go back over here, this point over here is the saturation region. So from here to here, this is the linear portion of your machine. So your machine was somewhere working at this point. So your machine was supposedly working at this point and it was producing this much EA. So over here, if I decrease it by 1%, showing it a little larger over there. So what will happen, since this is linear region, there will be a 1% decrease in also EA. Got it? So if you are in the linear region of your BH curve, your field current previously was IF, now this will change to IF dash. Your previous one was EA, now this will change to EA dash. So what happens? A 1% decrease in flux means a 1% decrease in EA. But again, this assumption is based on this condition that you are in the linear region of your BH curve, because this is a BH curve in front of you. Now going back over there, so what this means over here, that if a 1% decrease in flux is there, this is going to produce a 1% decrease in EA, assuming it in the linear region. So what was your previous EA? Your previous EA, which has been given to us, is 245 volts. But when we are going to decrease it, I am going to call it as EA dash. So what I am going to do it, I am going to have 245 minus 1% of 245. Okay? So there is a 1% decrease over there. So now this 245 minus whatever value, this comes out to be 242.55 volts. So what is now your new EA, or you can call it EAB. You, for simplest reasons, you can call it as EAA because this is at point A, and you can call this one as EAB also, so that this is your B point EA. Now corresponding to this EA, now for this EA, I am again now going to calculate IA. That is IA equal to VT minus EA divided by RA, and this is B, this is also B. VT is still the same because applied voltage is not changed. So VT is again now plugged in 250. Now this is 242.55, the value which we have calculated, and this is again 0.25, and this comes out. So IAB comes out to be, as per this book, this is 29.8 amperes. Please verify this if anyone has a calculator. So this is 29.8 amperes. Now what this is telling you, this is very important over here. This IAB equal having a 29.8 amperes. Your previous current was 20 amperes. What has happened now? You can see very closely over there that your IA current, which was 20 ampere, with a 1% decrease in flux, has now approximately 50% increase in the armature current. I'm again repeating, with a 1% decrease in the field current, that is corresponding to a 1% decrease in the flux, which is also corresponding to a 1% decrease in EA because we are assuming it in the linear region. So your armature current has now increased by approximately 50% increase over here. So what this means over there, if I go back to my this equation over here, that this flux and phi, this flux over here, this is the predominant quantity over here, and this one is the smaller quantity. So my torque induced is actually going to increase over there. Ji beta, question answered? Ji, any questions with this? I hope you have got this. I had a condition over here that your torque, phi and IA, they were having, torque was constant, flux phi was decreasing, IA was increasing. So I had to find out that which is actually the predominant quantity. So what I took over there, I took an example where VT is equal to 250 volt, EA is equal to 245, RA is equal to 0.25. So over here I find out IA equal to 20 ampere. So the machine is working in steady state at 20 ampere. So what I did in point B, I changed my RF resistance, or actually this is small f over there. You can change this to small f because this is changed by the resistance over there. So when RF is changed over there, your field current actually has decreased by 1%. Flux has also decreased by 1%. So corresponding to your BH curve or magnetization curve, your EA has also decreased by 1%. Previously, what was your EA? That was 245 volts. So now 245 minus 1% of it over there. So I have now 242.55 volt. Now when I plug this value again in this equation, I have now IAB over here equal to 29.8 ampere. And this is telling me that from 20 to 29.8, this is approximately 49 point something percent over there, or approximately 50% increase. So this means a 1% decrease in IA means approximately a 50% increase in 1% decrease in flux is a 50% increase in IA over here. So the torque is actually increasing. जी बेटा. एक सेकंड, वो भी आते हैं, उस पर भी आते हैं. This is the transient analysis which I am doing. अभी मैंने steady state पे नहीं जा रहा हूँ, अभी मैं जा रहा हूँ. So up till this point, what I have done now.
ये फाई का जो 1% है, वो ग्रांट के 50% से ज़्यादा नहीं हो सकता है.
एक सेकंड, I can't get the question again.
फाई की वैल्यू
एक सेकंड, मैंने एक कंडीशन अभी यहाँ बोली थी. आई एम इन द लीनियर रीजन, ठीक है. माई मशीन इज वर्किंग इन दिस लीनियर रीजन ओवर देयर. सो यहाँ पे अगर 1% का डिक्रीज 5% का भी आएगा तो EA में भी 5% का आएगा. सो कॉरेस्पॉन्डिंगली IA के अंदर उसके कॉरेस्पॉन्डिंगली, मैं टाइम्स की बात नहीं कर रहा हूँ, उसके कॉरेस्पॉन्डिंग आप करके देख लो. EA को आप इस दफ़ा 5% डिक्रीज कर दो and find out again IA will be tremendously increasing. So it will be again in the linear region. अगर ये linear region में नहीं है, then it will not take place. वो उसमें भी हम बात करते हैं अभी आगे जाके. Okay, so what has happened now? I am just copying this one, and since I have just concluded this one, so this is my over here. जी जी. मैं अभी आ रहा हूँ, एक सेकेंड, मैं आ रहा हूँ, एक सेकेंड, आ रहे हैं। देखो जी, व्हाट आई डिड ओवर हियर जस्ट नाउ दैट आई स्टार्टेड टू चेंज माई फील्ड रेजिस्टेंस, फील्ड करंट चेंज हुआ, फील्ड करंट चेंज हुआ, फ्लक्स चेंज, EA change, IA increased, and when IA was increased, flux was decreased, I have found out that torque has increased. Now, this is happening in the fraction of a second time. आपके पास you change your field resistance, आपके पास जब तक वो machine की value आती है, आप speed measure करते हो, it has gone through all that steps which I am talking over here. So steady state point वो है which is steady, it's not changing. आप ये light plug on करते हो, किसी पंखे को on करते हो, when the fan maintains a constant speed, that is a steady state point. लेकिन the point when you have turned it on and then the machine is taking a huge rise in current. आपने अक्सर देखा होगा, आप लोग अपने मोबाइल चार्जर्स को आप जब प्लग इन करते हो, those mobile chargers because of inherent quality inside it, they always spark whenever you plug in it. आपने अक्सर देखा होगा, कुछ भी नहीं है, it's just simple taking 0.2 ampere or 0.1 ampere, but they spark. They spark because of the capacitor inside it and because of the third harmonic inside it. That is all a transient response inside it. But afterwards, वो एक दफा चल रहे होंगे, it will never spark over there. So that transient current which is being taken up, the same transient current is going to be shown over there. So just let me finish this one so you get a little bit more answer into this one. So now when you have got your torque increase, ठीक है जी, अब क्या हुआ है, your machine was working at a constant load. मैंने लोड नहीं चेंज किया था, बट मैंने क्या किया था, मैंने फीड करंट को चेंज किया था. सो व्हाट हैज हैपेंड नाउ दैट व्हेन योर टॉर्क इंड्यूस्ड हैज इंक्रीज्ड, नाउ what has happened, your torque induced is now greater than T load. लोड टॉर्क से बढ़ गया, आपकी मशीन अब ज्यादा टॉर्क प्रोड्यूस कर रही है जितना रिक्वायर्ड है. उससे क्या होगा, what will happen, certainly because of this inequality, that is T induced greater than T load, your speed will go up. Your speed will go up. Now when your speed will go up, what will happen, when your speed has gone up, your EA will now go up by, because your K phi omega has now gone up. Your omega has gone up, so your EA has now gone up. This is all happening in steady state, in transient analysis over there. Now what has happened now, अब EA बढ़ गया, अब उससे क्या होगा, because of this one, your EA, when it will increase, this will now decrease your VT minus EA divided by RA. So EA has decreased, your current, increased on this one, this is increased. So EA has increased, so IA will decrease. So क्या हो रहा है यहाँ पे, what is happening, आपने जैसे ही फील्ड रेजिस्टेंस को बढ़ाया, फील्ड करंट कम हुआ, your flux also decreased, your IA increased, but now it has not decreased on. So what is going to actually happen, this whole process is going to repeat up till a point when your torque induced becomes equal to T load, but at a higher N speed. What is happening for this example? Let me see this one. I have over here on this side, supposingly I have this one as N, and here I have supposingly equal to, let me just not call it, I have supposingly time, don't let me call it over here at time t. So what is happening, your machine was working at a constant speed up till this point, ठीक है जी. What happened, at this point of time t1, what I did, I changed my field current. How I changed the field current? I changed my field current by having your field current or field resistance increase. What happened because of it? All the sequence of events take place and your current increase, then decrease, increase and decrease. And how this will change over here on the speed curve, this will change over here. This will go up and then have a steady state point after some point, and this speed will be constant ever here like this. This is the same response you are getting in your CAD course. I hope you have done up till now the RLC circuits and all that stuff over there. This is the same response over here with some damping effect taking place over there. So this is the same current increase. This is the same speed increase. आपकी speed बढ़ी, फिर वो वापस आ रही है, फिर जा रही है, and then this response over there which you are getting over here from within this time up till this point, this time is the transient response of your machine. उससे पहले steady state था, और ये steady state क्यों था? क्योंकि आपके सारे पैरामीटर्स कांस्टेंट थे. आपका लोड कांस्टेंट था, आपका फील्ड करंट सेम था, इट वाज नॉट चेंजिंग. मैंने इस पॉइंट T1 पे क्या किया है? व्हाट आई हैव डन ओवर देयर, आई हैव चेंज्ड माय RF रेजिस्टेंस इंक्रीज की है, जिसकी वजह से फील्ड करंट कम हुआ है. फील्ड करंट कम होने की वजह से मेरी स्पीड जंप अप की है बिकॉज ऑफ ऑल दैट सिनारियो व्हिच आई जस्ट गिवन ओवर देयर, एंड देन it will follow and damp out over there. This damping depends upon the moment of inertia of your machine. If your machine has a huge mass, has a huge torque, a large size, it will take some time because एक दफ़ा आप उसकी स्पीड इंक्रीज कर दोगे, उसको वापस लाने के लिए you require some time. So जितनी छोटी मशीन होगी उसका रिस्पॉन्स उतना ही छोटा होगा. Now your lab machines are very very small, just 400 watts, nothing special. So that's why when you change your field current, the response is quick over there. But if you are working on something megawatts or kilowatts of machines, this response will take some time because of the inertia of your machines over there. So this is your speed over there, and same thing if I can plot over here for current IA. जी कोई बताएगा मुझे IA के साथ क्या होगा? If I have IA and this is time t again, जी can anyone tell me what will happen on the, if IA was supposedly working up till a constant line? नहीं एक्सपोनेंशियली कैसे होगा? दिस इज टाइम T1. एग्जैक्टली सेम. वाई? बिकॉज स्पीड कहाँ से आ रही है? IA करंट से आ रही है. जितना IA ज़्यादा होगा उतना स्पीड भी ज़्यादा है. सो इट विल एग्जैक्टली फॉलो a same behavior, but this time it will now have a different steady state point afterwards. Now this is for your speed, and if I draw it for your torque over there, if I have it for the torque, if I draw it for your torque, this is your induced torque and this is your time t. How this will change? Supposedly this was having a constant value over here and constantly it was going over here at T1 point. What will happen? What will happen after time T1? Steady state point क्या होगा? क्यों? It will first of all increase, then decrease, but it will stable itself at the same torque. क्योंकि लोड हमने नहीं चेंज किया, मशीन अभी भी उतने लोड पे काम कर रही है. सो व्हाट विल हैपन ओवर हियर इफ आई ड्रॉ दिस वन, दिस विल फर्स्ट ऑफ ऑल इंक्रीज एंड देन इट विल सब्सिडाइज अगेन सेम टॉर्क. This oscillations period is actually the transient response of your machine, and all these steps which I have shown you are the transient responses which are happening inside your machine. Now coming back to your torque speed curve, now how that torque speed curve will change? Now if you have over here the, let me draw that curve again, sorry, on this one. So I have this one as speed, this one as torque, and over here if I have, now if I have, this is my equation. Now at this particular point I had omega naught and this omega naught was corresponding to Vt by K phi. ठीक है जी. Now this is for RF1. What is RF1? The field resistance, let me call it R small f1. I always take this mistake. So this is RF1, which means the resistance was some value, 1 kilo ohms plus some shunt resistance. Now I have increased that RF1 to RF2. So this means now I am going to plot it for RF2, which is certainly greater than RF1. So now what will the curve look like now? ऊपर होगी या नीचे होगी? ऊपर होगी, नीचे होगी, किधर होगी? Gee, what will happen? First of all, y-intercept. What is y-intercept? Vt by k phi. So will it be higher, lower? Denominator value is decreasing. Denominator value is decreasing, so y-intercept value will be larger. So this means that actually I have done this a little up. मैं इसको थोड़ा सा नीचे ले आता हूँ so that I can draw the above curve over here, and this is over here, and this one, sorry, on this one, and so now over here this curve will be starting supposedly at this point, and this will be corresponding to omega 1. This will be equal to Vt by k phi dash. What is phi dash? Corresponding to RF2 certainly. And now what will be the slope? y-intercept ऊपर आ गया, slope के साथ क्या होगा? Slope की वैल्यू क्या थी? माइनस RA डिवाइडेड बाई k phi होल स्क्वायर. जी, स्लोप के साथ क्या हो रहा है? स्लोप की वैल्यू भी माइनस नेगेटिव है. इट्स गेटिंग मोर स्टीपर. It's getting more steeper. So overall, this curve is now going to be like this, and this will be RF2. So you can see now your machine, if supposedly your machine was working at any different point, supposedly if your machine was corresponding to this torque over here, what happened? Your previous machine was working at this value of your speed, let me call it omega 1, and then afterwards this changes to omega 2. So by change of your field resistance, your omega has changed to omega 1 to omega 2. Now the same curve with, I just want to complete it, I don't have much time. They have a class after just 9:25? Okay. Let me just complete it, because if I don't complete this point, this is going to be difficult to understand afterwards. So this last point over here, that if I have this curve over here, and if I extend this curve over here, let's see this very carefully, and if this curve, I have extended it over here, and I extend this curve to the, and I extend this curve also here. Now these two curves, when they are extended, now when I have extended this one, what this means, when they are reaching the x-axis point, this axis point where they are actually reaching it is actually called as the stall condition. What is the stall condition? Standstill. The motor rotor has been stalled. It is not moving, it's not being allowed. But before this condition is there, if you see very closely over here, this point is the intersection of these two curves. And why this is happening over there? Can anyone answer this one? Because after this point, the concept that field current is proportional to 1 over n is not true in this region. Previously, what was happening in this region? Your field current was proportional to 1 over n. Why? Because field current was decreased, speed was being increased. But after this crossing point, why this is not happening? Can anyone tell me? Yes, the point is it that you are actually now approaching stall condition. Your speed is so small that now the point which I actually showed you in the very first start, this curve over here, that was the green color curve that was corresponding to a very, very low speed. So a change in phi is not having the same change in Ia now. So it's not now in the linear region. So this condition where I have just told you about this one, that k phi Ia was there, now a decrease in decrease in this one over here and a increase in this one, they are not being predominant. No one is predominant over there. So the torque is not increasing there because now you are approaching the stall condition over there. But this condition of stall is only possible when you are approaching a machine, that is, supposedly machines are designed up till this full load point over here. They are not designed beyond this full load point over there. So this portion of the machine which is shown over here is only possible in some special machines. Practically, you will always go or remain inside this machine over there, which is easily telling you that your field current is proportional to 1 over n or inversely proportional to n over there. Please kindly go through this one. This is article number, I guess, 8.4 from your chapter. And based on this one, please, I've just missed one topic over there. I don't have time. I was also a little late. So hopefully I will add this one in the recording part over there, or maybe in the next lecture, because that's very important. So, कब का वो तो पिछले लेक्चर में ख़त्म हो चुका है कब का क्या हो गया जी जी Okay, so now we have to move on towards the armature voltage control, which actually is the second method for the speed control of DC shunt motor or a separately excited motor. We have just done the speed control for the shunt was separately excited, and the method was changing the field resistance over here, and this was a little difficult method, but overall it was having a very good response over there, because when you are changing the field current, you are having an inverse relationship with the speed over there. So when you are actually decreasing your IF, your N was actually going to increase over there. So now the second method of speed control, which is actually armature voltage control, means over here, if I go back to your shunt motor over there, now shunt motor and separately excited motor, they both have one common thing over there. They both have the same motor equation over here. Now coming to the armature voltage control, as the name suggests, it has armature inside it, the word armature. So this means that you have to actually change the voltage across the armature, which means you have to change the voltage across A1 and A2. You don't have to change this voltage over there, because if you change VT, you are actually also changing the field current inside the field winding. But yes, if this machine was a separately excited machine, then certainly you are going to actually power your armature through another voltage supply, and then you can actually change your VT and then you can have it, because then this connection with the same supply would not be there. So this is generally called as an armature voltage control, because if it was separately excited, then this means you are actually changing the armature voltage. And if it is shunt over here, shunt motor over there, as shown in this diagram, here instead of changing this VT, we are actually changing having a power electronic device over there. This box over here is actually a DC supply, which is actually going to, or DC input and output, so it's actually going to change the voltage that is actually going to be feeded in towards the armature. So in other words, you are actually only changing the voltage which is actually going to be provided here and here, that is A1 and A2 terminal. Now in practically in the lab, how you have been doing this one, you have been actually changing this VT, but at the very same time you have been changing this R shunt resistance, so that the field current that remains same. In other words, you are actually doing the same thing over there. So when I come to the armature voltage control, we know the speed equation, the same speed equation we did in the previous speed control. Omega was equal to Vt by K5 minus Ra divided by K5 whole square, torque induced over here. Now this easily tells us that when you are going to actually change the armature, more current Ia is going to flow in. So this certainly means that you are actually going to have more applied torque, or more torque is going to be produced over there. So very simply over there, since you are not changing your Ra, you are not changing your K, you are not changing your flux phi, so what is actually thing which is actually going to change over there is actually going to be the Vt. Now this Vt, you can call it in armature voltage control, you can actually call this one as actually Va, because Va is actually the voltage across the armature. But since if it was a separately excited, then this will be called as Vt or Va. So this equation over here, if you can see very closely, that this portion over here, this is the y-intercept over there. So there is no change in the slope, there is no change in any other quantity. The only thing changing is over here is Va. So very simply over there, if I have two voltages Va1 and Va2, this means that if my Va1 is certainly larger than this, so I will be having this one, and Va2 will be something like this one. You can see both slopes are exactly same over here. Why? Because the slope of this curve is minus Ra by K5 whole square. So this is easily telling you that if your machine was supposedly working at this much torque, let me make that torque line over there. So if this is the torque line over there, so corresponding to this torque over there, you will be getting this much speed. and corresponding to this one. So if your requirement of torque was equal to this value, so you were supposedly getting omega 1, so now you will be getting omega 2. So this means by changing your applied voltage, that is actually the armature voltage applied across A1 and A2 for any of the two machines, you are actually changing your speed, and this is totally directly proportional, which means that you are actually having VA proportional to your N or omega, same thing over there. So this means that armature voltage control, increasing the applied voltage on the armature, you can actually change the speed very easily. Now this is actually a very brief overview on armature voltage control. What actually happens inside a machine, just like we did it for the field current control, what happens over there, you actually change your VA, which means you are increasing your VA. What happens actually, since IA is equal to, this is actually again same VA or VT, I'm using it interchangeably over there, because if it's a separately excited, then it will be VT, and if it is going to be a shunt, you can call this one as VA or whatever. So this is VT minus EA divided by RA. So what this happens, VT has increased or VA has increased, the current IA has increased, and when current IA has increased, your torque of your machine will increase, because torque is equal to K phi IA. So if your current is increasing, your torque is increasing. The other quantity phi is constant. Why? Because you have kept the field current inside the field winding as constant over there. Even if you were changing VT, just like in your lab experiments, you are having a R shunt resistance, so that keeping the field current constant over there. So the overall current IA is increasing, and when that current IA is increasing, your total torque is increasing. Now when the torque is increasing, this is certainly going to go beyond your load torque, which is the demand of your machine. So this means T induced is going to be greater than T load, and when this happens, as we have done before, that your speed of your machine will increase. Now speed of the machine has increased. What this will do, this will have again an effect over there, which means that K phi omega will increase. Why? Because K phi omega is EA, omega has increased, phi is still the same, K is still the same. So what will happen? EA will increase. So all these steps again, just like in field current control, we are having over here an EA increase, and then this EA increases, what happens? IA now decreases down. So now when this will decrease down, this will have again an effect of torque reduction over there. So this process will follow on up till the point when T induced becomes equal to T load, which is actually the steady state point for that machine. And again, just like your field current control method, you are going to have a speed change over there. So your machine was supposedly working at 800 RPM. At time T1, what you did that armature voltage control. So there will be going to be a small transient period, and then you are going to get a constant speed, but again a higher value of speed over there. And certainly you can call this omega 2, this one is omega 1. So this means by increasing your applied voltage, you are increasing your speed, and your machine is now working at a larger speed as depicted by this diagram over there. So if you were working supposedly at VA2, now you have increased it to VA1. So what happens? Your speed has increased from omega 2 to omega 1, or you can convert them into N2 and N1 over there. So this is your armature voltage control, and this is easily telling you that this whole process, as we have done it for the field current control, this process will continue to on until and unless your T induced becomes equal to T load. And the same schematic, that this damping effect is going to be dependent upon the size of the motor and how the machine behaves over there. And this will be coming at a constant when this will be running at a new speed omega or N, whatever units you are measuring your speed into. So this is the second method of speed control, which is called as the armature voltage control, by which you are actually changing the armature voltage, or in other words, you can change the applied voltage for a shunt motor or a separately excited motor, but keeping the field current constant, maybe by using a shunt resistor or maybe some any other resistor which we have added inside its path. The third method of speed control, which is very crude form, is actually inserting a resistor in series of the armature. What this means over there, the same diagram as you can see over there, but what I have done over there, with the resistance of the armature, I have added another resistance, maybe variable, maybe fixed. I have added in resistance R. So now this small so capital R with this A as capital again over here, this is called as RA. So what I have done over here, I have added an additional resistance apart from the resistance of the armature armature winding. So the total resistance is now Ra. And by simple circuit analysis rule, I guess if you easily understand this, if on these 2 points, if this is A1 and A2, you were applying supposedly 160 volts over there. So now whole 160 volts are not going to be applied to the armature. There is going to be some drop across this R. So practically what will happen, the applied voltage on the armature is going to decrease, and also the current which is flowing over here as IA is actually going to decrease for obvious reasons, because you have a resistor added. Now this resistor added is going to be something comparable to the resistance of the armature, which means that this R, if RA over here is equal to 8 ohms, just like our lab, this R will not be more than like 3 to 5 ohms or 6 ohms, something like that. So something R added over there. Now why I called this one as crude, because adding a resistor in series means that this is actually going to have a lot amount of power wastage. So if supposingly if the motor is loaded and it's running over here, and here is a current of 3 ampere to approximately 4 ampere flowing over there, so this resistance, if I calculate the power rating of this resistance, this will be equal to P equal to I square R. And if that resistance is supposedly 3 ohms and there is a 3 ampere current, so this means that you are actually having 9 cross 3, 27 watts of power wasted over there. This is the actually power wasted. The total efficiency of this system is decreased down. And if I see it on the overall speed chart over there, we know omega, the same formula for omega over here, that is Vt by K5 minus Ra divided by K5 whole square, and then the torque over there as a variable. You can see very carefully over there what I have done. I have changed this Ra to now small ra, which is actually Ra plus capital R. So what this means, what was this factor over there? This factor over here was the slope. So what this means, that your slope has now become more negative. Negative sign telling you that the slope is decreasing over here. So this has become more negative. So previously if my curve was something at this Ra, so if this was something Ra, now this will become more steep over there. So now my resistance has now become equal to Ra plus R. That is actually an additional resistance added over there. So what happens over there, if your machine was working at this torque, previously this was producing omega 1. Now by adding a resistor in series, you have to actually change that speed to omega 2 over there. Now there are two problems of this method. One problem, very important one, you are wasting a lot amount of power over there, as I just told you. The second thing, if you want to add a resistor in series over there, and if in the first case you never added it, you have to first of all stop the motor and then do it. So this is actually a little crude form over there, that if you want to add it, unless and until you have a variable resistor where you can actually make it from 0 to some 3 ohms or 4 ohms or whatever value you want to use it, then, but variable resistances are very expensive, and certainly very expensive if the amount of current flowing through them is very, very large. So this method of inserting a resistor in series of the armature is not very effective. Why? Because it is having a lot amount of power loss, and secondly you are inserting it in path over here with the series, and if you don't have any variable resistor control, then it's very difficult to actually stop the machine and then again add that resistance over there. So your speed torque characteristics is something over here having the same point, because the applied voltage is still the same, that is Vt. They both have all the same Vt by K5, but the slopes are changing. So this one is certainly having more slope as compared to this one. So certainly this method, again inserting a resistor, it's a crude method, but still it's a little obsolete. But sometimes there are places where you want to actually use this method, because sometimes you don't want to spend that much on the previous two methods, which was the armature voltage control and the field current method over there. So instead of having that much apparatus and all that variable supplies, you want to just add a resistor in series and get a little bit variation in speed. That is still justifiable for small motors if cost of electricity or power dissipation is not an issue for you. But for a longer run, if you want to run your machine, that's going to be a bit problematic if you are a very efficiency hungry person or a manufacturer over there. Now, since we have done just these through three methods of speed control, which I have added over here, one is the field current control, the other one is the armature voltage control, the C part is the inserting a resistor in series with the armature. Now very, very importantly, which method to use where. Now this is very important. Now the A method, as I just told you, that I had field current inversely proportional to N over here, and this armature voltage was proportional to N. So what this means over here, that if my field current is increasing, my speed is actually going to decrease down, and if my armature voltage is increasing, my speed is also going to go up. Now, which method to use where? Now, before I install these two methods, now these two methods are the most ones used over there. The last one, as I told you, is not used nowadays, only until unless here that your industry is having a very small machine and small expense to use it, then you use an inverter by inserting a resistor in series with the armature. So which method to use where? From the A and B part, that is the field current control and the armature voltage control. So over here, what you are going to do over there, I have what is base speed. Now, since all of you have done experiments in the lab, our base speed, as I told you, or the rated speed in our lab for our motors is approximately 1500 RPM. And you can achieve this speed by having approximately 160 volts applied to your armature. So your machine will be running at approximately 1500 RPM at your no load. If you apply some load, certainly, and if there is a generator coupled with it, even if it is not connected, it will be still taken as some load or some mass working over there. So a motor which is applied its rated voltage and it is running at its nameplate rating over there, nameplate speed over there, that is called as the base speed. Now, supposingly you want to change your motor speed from 1500 RPM to something like 2000 RPM. Now, what you have to do? So we know that you have B method where you can increase the armature voltage and you can increase your speed. So this means that by increasing your speed, you can do this by VA. So you can increase your VA and you can go to 2000 RPM. Sadly, that is not possible. Why? Because at 1500 RPM, your armature voltage is already 160 volt and that is the rated voltage of your machine. So you cannot go beyond it. If you go beyond it, you are actually going to damage the windings of your machine. So practically, this method of VA control is not applicable when you are going on from 1500 RPM or from the base speed. This is actually the base speed. Let me write it on over here, base speed. So you cannot use this method for the speed control from base speed to anything higher, maybe 2000, maybe 2500. Okay, so you have to now have the base speed increased from 1500 RPM to 2000 RPM. So here the method of field control will be actually coming into play. What I mean by this, since I know that field current, when it increases, my speed decreases. So now what I am going to do, instead of increasing the field current, if I decrease my field current, my speed will increase. And this is the same thing I want over here. So if I will decrease my field current over there, my speed will increase over there. And decreasing the field current will have no harm over there, because the field current, even if it is flowing at the rated value at the base speed, it will have no effect of decreasing it down. So at base speed, supposedly your field current was equal to 200 milliampere. So now even if you make it something equal to 100 milliampere or maybe something intermediate value, you are going to have from 1500 RPM to any other value of 2000 RPM, you can increase your speed. So this means that the field current control method is used for the speeds where you want to go beyond your base speed to any other higher speed. And the second method of control, where you want to go from 0 to your base speed, this is the point where you have to actually use your armature voltage control. Why? Because armature voltage control, if you increase it from 0 to the rated value and certainly within the rated value on the nameplate, this will still run. But you cannot use this field current method on the base speed below over here. Reason again, for the very same reason, if you are at 200 milliampere already at the base speed and you want to reduce your speed, you will have to increase your field current, and you cannot go beyond 200 milliampere because you will burn the windings over there. So 1500 RPM is the base speed as in your lab. So if you want to increase it from above the base speed, so you will use your field current control, and if you want to go from 0 to 15 RPM, you will use your armature voltage control. So this means that now we have a rule that field current control will go from base speed to the higher speed, and armature voltage control will go from 0 to base speed over here. So both these methods have now a significant space where they are actually going to work on this one. Now, when we have decided on which machine or which method to use where, now coming to the characteristic curves of your machine. Now, what are these? Listen to this very carefully because this is very, very important. Now, what I mean by characteristic curves is actually these are not the curves for any particular machine. They are telling us that how the machine will behave when the load is going to apply, that is the capability curve. Just like whenever you are in industry and someone has asked you to actually make a design of your industry and you want to actually select some machines for your industry, so you are actually going to see that okay, you want to run that machine at what speed and what torque. So you are actually going to see the capability curves of your machine. So similarly, if you see very closely over here in this first graph, what I have done over here, on the y-axis I have my maximum torque and on the x-axis I have my speed. Now from 0 to base speed, it's certainly going to be armature voltage control, and from base speed to whatever maximum value that is dependent upon how the bearing is going to behave, that is actually going to be the VF control, or actually you can call it also as IF control, because field current control can be controlled by the applied field voltage also, or if it is in a shunt motor then you can do it by the IF control. Now what is this curve over here which is actually following a straight line here and then it is going exponentially down? Now if you very closely see over here, this is a straight line. What this means, these are capability curves, and we know torque is of any machine is equal to K phi I max. Now when you are increasing your machine speed from 0 to some base speed over here, this means that your speed is going to increase from 0 to over here. Now in this region, when you are using your VA control, what is the space, what is the torque that you can actually get out of your machine? I'm not talking about the load that you can apply. I am asking how much torque you can get out of your machine. If your machine is going from 0 to some base speed value, that value is constant. Why it is constant? Because torque is equal to K phi. Now when you are applying VA control method, your flux phi is constant, it's not changing, and IA max, your IA max in our lab machines is going to be dependent upon the winding it can handle the current. So in our lab, the windings can handle 3.5 ampere current. So this means that the torque formula is only dependent upon K phi IA. So this means it is not dependent upon the speed which is changing over here from 0 to the base speed. So this means that your torque will remain same throughout over there. Now does not mean that the torque will remain same from the machine. This is the capability curve telling you that your machine is capable of producing a constant torque out of, even if it is running at 200 rpm, 500 rpm, 600, 800, or even 1500 rpm. If 1500 is the base speed, you can get the same amount of torque from your machine, because even if you are running at supposedly 200 rpm, you can have 3.5 ampere current or whatever the rated current flowing inside your windings. Flux phi is constant, it's already at the maximum value. Your K is machine constant, your torque is maximum. So if you repeat it at 200 rpm, over here, and even if you repeat it at approximately 1200 rpm, the torque will remain the same, which means that you can have a machine loaded up till its maximum torque in this VA control method. But when you go beyond this point, which means you go beyond your base speed to some higher value point, you are actually now using IF control or VF control method, which means that your flux phi is actually decreasing. So now when flux phi is decreasing, your torque is going to decrease. And since we know from your BH curve that when your field current is decreasing, your flux phi is not going to be actually linear. It's actually going to be an exponential decrease over there. So you can see in this region, the torque that can be output from your machine. This is again, remember, these are capability curves or characteristic curve. They are dependent upon the capability of your machine that it can provide. So your machine can only provide a reduced amount of torque if it is going beyond your base speed over there. If you are working at a very higher speed, you can only get a limited amount of torque over there. But if you are working in the speed range of 0 to base speed, then you can have the maximum torque, that is actually the capability of your machine taken out at any speed from 0 to base speed over there. Now one term written over here, that is P max constant, that is dependent upon the second curve over here. And if you see this curve over there, this curve instead of torque over here has the maximum power over there. Now what is that maximum power? The power the supply is being given or is being giving to the motor over there. Now in this VA control method, which was over here, that VA control method, you are increasing from 0 to the base speed. So in this region over there, you know power is equal to tau omega. So if I am talking about P max over there, this will be equal to T max into omega m. Now what is T max? T max is constant value. It's not changing over there. The only thing that is changing is omega m, because I have on the x-axis 0 to nm. You can convert nm into omega m. So this means from 0 to the base speed, your omega m is increasing. That's why this is a linear line over here, increasing linearly depending upon how the x-axis is changing you have over here. So P max is equal to T max into omega, and T max is constant over here in this method. So when you are increasing your machine from 0 to base speed by using VA control method over here, your power maximum is limited, which means that P max is going to be increasing as you increase your speed, and it will go up till a maximum point that is at the base speed. But now when you will reach your base speed, that power will become constant. Why? Because now you are going to use the VF control. And when you are going to talk about VF control, what you are going to do, you are actually going to decrease down your flux. And when you are going to decrease down your flux, what will happen? Your current IA is actually going to increase. So the torque will remain the same the power maximum will remain the same. Torque is actually practically decreasing over there. So in this equation over here, when torque over here is decreasing, speed is increasing, keeping the P max constant over there. This is very important one point over here, because from this point onward, when you are increasing your machine from a base speed to any higher speed, your torque is decreasing. So this means this term is decreasing, your speed is increasing. But since the load on the machine is still the same, so the power output is constant over there. So machine cannot go beyond this point, because whenever the manufacturer made that machine, he designed that machine at the base speed. So this point is the power that achieves over here. That is the maximum power it can handle. So this is the maximum power it can handle at this particular point. So this is going to be a straight line over there. But if we talk about the maximum torque, this is something like this curve. And when we are talking about the P maximum, this is something like this curve. So these two curves are very, very important whenever you are actually in the process of selection of any machines for your industry. So you have to handle that. How supposedly you are going to select a shunt motor for your machine, and maybe your boss has actually asked you, okay, you have to select a machine that is approximately at 1600 rpm. You should have approximately 10 newton meter of torque. So you will see, okay, the base speed of my machine is 1500. So at 1600, can I get that much of torque over there? If that is done, then you are going to select that machine. So these capability curves are going to come with your machine. So you are going to select that how much torque you would require. Then you know which speed at which you are going to work it. Now it's not possible, supposedly you wanted something at 1800 rpm, the same torque, but at this one you are only getting this much torque, but you required this much torque over there. So what will happen? The torque will not be will be fulfilled. So there is going to be a problem over there in your machine. So this is very important that your characteristic curves or capability curves of your machines, whenever you are selecting machines for your industry or anywhere you are working, you have to go through these capability curves. Last thing, but not less important, is the field loss relay. Now I told you in the very start of this lecture that there is one problem which you have seen in your lab, that because of vibration sometimes you have like 4 wires coming out of it. Supposedly I just make those 4 wires over there. You call this one as A1, A2, this one as F1, F2, and by chance, supposedly the 4 wires which are going inside it over there, one of the wire actually gets out, and that wire is field wire. What happens because of that? The motor suddenly stops, and you don't witness any other thing. You just see it, and when you try to again plug it in and you just again try to have it run again, you are actually going to have a problem that your fuse is burned down. Now, why this happens over there? For this one, there is a legitimate reason over there. Why? Because when the wire actually is due to vibration, it takes out or it's cutted by due to some other reason, this field current becomes equal to zero instantaneously. So what happens? The speed will approach infinity theoretically. Theoretically, your field winding current will approach zero, and since this equation holds true, your speed will approach infinity. But for infinite speed, you require your current IA to also be infinite, because the motor is actually trying to move up to a very higher speed. It will require infinite amount of current. But before that current is reached, your fuse which you have actually placed over there, it will actually going to be burned. So I hope you are getting the point that why I have asked you, or Ms. Tarina in the lab is actually asking you that you are actually going to have one group member actually taking into control that any of the wires, especially from the field winding, does not get out, because if that happens, your field current becomes zero and your speed approaches infinity, and your current approaches infinity as far as theoretically is concerned. So this fuse actually gets burned. Now, this is a very big problem. So what happens? Here comes actually a very important relay, a field loss relay. And as the name suggests over there, that you are actually going to put this relay inside the circuit of your DC shunt machine, so that whenever a field loss relay is going to detect that your field current becomes equal to zero, it's actually going to make the supply turn off. So what I mean by this, if I go back on your shunt motor circuit diagram, let me take circuit diagram from over here. So if I have this circuit diagram over here, so if this is my circuit diagram, let me take it over there on your field loss relay point over here. So if I have over here, now in this one, let me take off this VA over here. So if you see over here in this diagram, what is happening, you are actually, let's suppose our shunt is also not there. So what I am going to do over there, this is going to be a field loss relay. I'm just using abbreviations over there. So this field loss relay, when it is going to detect over here that field current when it becomes equal to zero, this is going to have a small switch over there, and that switch over there is actually going to be activated by this field loss relay. And as soon as it senses that the field loss relay becomes equal, or field current becomes equal to zero, this switch will be turned off. What I mean by, I have actually used, so this will be turned off over there. Previous position of this switch would be something like this, but as soon as this relay will sense that field current has gone to zero, it will instantaneously turn off. Now what is the advantage of doing this? The advantage is this, that infinite current will not try to flow from over here. And when infinite current will not flow, your machine will be saved. Now in our lab, you have fuses over there, because the current going through the armature winding is not more than like 3.5 ampere. So a 4 ampere fuse works very well and over there. But when you are working in the industry and you have very, very big machines over there, which are taking hundreds of amperes of current, even before the fuse can actually work or any other protection scheme can work, the motor will be damaged. So to avoid that damage over there, field loss relays are very, very important for big machines, because they are actually going to detect that when your field current goes to zero, this is going to be a small circuit breaker over here, and this circuit breaker will be turned off. So this armature current or the load current will not go to infinity. It will be stopped instantaneously as soon as it is going to detect, and your machine is going to be saved from any damage. Because if even not infinity, even if like 2 times the rated current flows through this armature, it's going to be damaged. The winding is going to be open circuit, it's going to melt down, or it's going to have a winding failure over there. So field loss relays, very, very important in the industry, especially for large DC machines. So this field loss relay comes in the field circuitry, and it is connected over here in series with the field winding, and you are detecting that whenever the field current becomes equal to zero, it will turn off the circuit breaker, or maybe just give a signal that circuit breaker may be relay or maybe a magnetic contactor or anything, something like this. So it will actually take off the supply off totally and save your machine from damage. So this is a field loss relay over here. So this is all for today. I guess we have talked about the speed control methods over there. We talked about the field current control. We have talked about the armature voltage control method over there. We have talked about inserting a resistor in series of the armature, and we have also talked about which method to use where, and very important one, the characteristic curves or the capability curves. And in the last, we have talked about a very important thing, that is field loss relay. Thank you.